Hello students, welcome back to Math 251. Hope you are having an amazing day. This is section 3.4's lecture video. Last time, if you recall, we learned how to find derivatives of polynomials using what we call the sum rule and the constant multiple rule and the power rule. So far we can take derivatives really easily of polynomials. We also learned the derivative of e to the power of x, so we can take derivatives of functions involving that as well. Today we are going to learn two more rules to find derivatives of more functions, products and quotients of different functions. But first, our mathematician of the day is Lev Pantrygin, who was a 20th century Russian mathematician who was blind due to a stove accident. Nevertheless, he became one of the best mathematicians of his time, and his mom often helped him by reading aloud math books. Pretty amazing. I cannot imagine learning math without being able to see it. That's amazing. And did you know that our Hindu-Arabic number system began developing as early as the 1st century? Numbers have been around for a long time, including our numbers that we use. So yes, today we will be discussing the product and quotient rules when it comes to finding derivatives. The first one we'll do is called the product rule. So if f and g are two functions, and they are differentiable at the point x, then I have that the derivative of f of x times g of x, so the derivative of the product of these two functions is equal to the following: f prime of x times g of x plus f of x times g prime of x. Now, it doesn't matter which of the functions we label f and g, as we will get the same result no matter which function we label f and g, but this is how we can take the derivative of two functions that are multiplied together. So let's do an example. Let's find the derivative of h of x is equal to x cubed times 4 square root of x plus 1. So I am going to call f of x, x cubed, and I'm going to call g of x 4 square root of x plus 1. Now, in order to plug into the product rule, I also need to find f prime of x and g prime of x. So using the power rule here, I see that f prime of x is equal to 3x squared. If you remember from our lesson on Monday, we don't know how to take the derivative of a square root using the power rule yet, but if you remember, the derivative of the square root of x, just so we don't have to do it all over again, is 1 over 2 square root x. So that means that g prime of x is equal to, I take 4 times the derivative of square root of x, and the derivative of 1 is equal to 0. So this is 4 times 1 over 2 root x, since the derivative of square root of x is 1 over 2 root x. If you're not sure where I got that, I would suggest going back to section 3.3. We did that derivation last time. And simplifying this a little bit, this becomes 2 square root of x. Okay, so actually, you know what? This is not 2 square root of x, sorry. So this is 4 over 2 square root of x. So this is 2 over square root of x. Sorry about that. Okay, so now we have f, g, f prime, and g prime, and we can plug it into our formula. So the derivative of x cubed times 4 square root of x plus 1 is equal to f prime of x, which I found to be 3x squared, times g of x, that was one of my original functions, which was 4 square root of x plus 1, plus f of x, which was x cubed, times g prime of x. G prime of x we found to be 2 over root x. So this is the derivative of our original function. If you would like, you could factor out an x squared from both terms, but I'm just going to leave it like this. So 3x squared times 4 root x plus 1 plus x cubed times 2 over root x. This is the derivative of the original function. Pretty cool, huh? All right, I'd like for you to try example number 2 on your own before we do it together. So go ahead and pause this video, give it a try, and then come back and watch me do it. All right, hopefully you've tried this on your own. So we have r of x equals x squared times e to the x. So I'm going to label my two functions, f of x equals x squared, and g of x equals e to the x. Again, it doesn't matter which one you label as f and which one you label as g, you'll get the same result. So then, f prime of x is equal to, using the power rule, 2x, and g prime of x, the derivative of e to the x is e to the x. So if I plug into my function, my equation for this, I get that the derivative of x squared times e to the x is f prime, which is 2x, times g, which is e to the x, plus f of x times g prime of x. And I could leave it just like this if I wanted to, but I also see that I could factor out an x times e to the x of each term. So if I factor out x e to the x, I'd get 2 plus x. So these two are both correct, but one of them is just a little bit more simplified than the other. So this is the product rule, and I would get real comfy with it because we are going to be using this for the rest of the term. So yeah, hopefully you are feeling pretty good about using this. Next, we are going to learn the quotient rule. So if f and g are differentiable at x and g of x is not equal to 0, then the derivative of f of x divided by g of x is equal to g of x times f prime of x minus f of x times g prime of x over g of x squared. When we are using the quotient rule, it does matter which one we label as f and which one we label as g. We will not get the same result if I accidentally switch them up. So my f always has to be the function that's on top, and my g always has to be the function that is on bottom. I know that some people have cute little ways of remembering this. My favorite one is, so if I call g low and f high, it's low d high minus high d low, square the bottom, and away we go. Low d high minus high d low, square at the bottom, and away we go. Anyway, I think it's pretty cute, but if you just want to memorize it straight up, or if you want to come up with another way to memorize this, that is obviously fine as well. So let's try this quotient rule out. So I want to find the derivative of f of x equals x squared plus 2x plus 2 over x squared minus 4x. So I label my top as f of x. So f of x equals x squared plus 2x plus 2. And g of x is the bottom. X squared minus 4x. And I need the derivative of each of these. So using the power rule, I get f prime of x equals 2x plus 2. And g prime of x is equal to 2x minus 4. Now our equation is the derivative of f of x over g of x is equal to g of x times f prime of x minus f of x times g prime of x over g of x squared. So if I plug in all of these pieces now, my first one is g of x, which is x squared minus 4x. X squared minus 4x. F prime of x is 2x plus 2. Minus f of x, x squared plus 2x plus 2. I'm going to run out of room here. Minus x squared plus 2x plus 2 times g prime, 2x minus 4. All of this over g of x squared. So that's x squared minus 4x squared. Okay, now this is 100% correct. If you wanted to leave it like this, that would be fine. If you were to do a bunch of algebra and simplify it by expanding these two terms on the top, like this, etc. So expanding all of it out, you would get the following. Negative 6x squared minus 4x plus 8 over x squared minus 4x squared. Again, the top one, this one, is correct. And in fact, on exams, when you are asked to find the derivative of something, you will most likely be asked to leave it in the unsimplified form. But sometimes if you are trying to compute something, like if you were to plug in an x value, it would be easier to simplify it and then plug in the x value. So again, either one of these is correct. It kind of just depends on what the question is asking for. All right, example number 4 is also using the quotient rule. So go ahead and give example number 4 a try on your own before we do it together. So pause this and give it a try. All right, let's do number 4. So my top function is f of x, which is, in this case, e to the x. That makes f prime of x also e to the x. G of x is my denominator, which is 5x squared. And that makes g prime of x equal to, using the power rule, 5 times 2x, which is 10x. So then the derivative of my original function, d dx of e to the x over 5x squared, is equal to g of x, which is 5x squared, low d high, so the derivative of the top, which is e to the x, minus high d low, so minus the top times the derivative of the bottom, which is 10x, square the bottom, and away we go. In this case, it's pretty easy to simplify this a bit. If I look at the top, I can factor out a 5x from each of the terms on the top. So if I do this, I get 5x times e to the x actually is what I can factor out. And I will be left with, let's see, x minus 2. All of this over 5x squared. And then, yes, if I wanted to, I could also cancel out one of the 5x's as well, but I'll just do it like this. But this is also correct. I just simplified a little bit because I like things to be nice and neat. But the first one is correct as well. Okay, next we want to find an equation of the tangent line to the graph of f of x equals x minus 5 over x squared plus 1 at the point 1, negative 2. So I'm going to have to use the quotient rule here because I want to find the derivative of this function at a certain point. So I'm going to use the quotient rule in order to find that derivative, and then I will plug in my point to find the slope of the tangent line. So my f of x, my top here, is x minus 5. My denominator is x squared plus 1. Taking the derivative of the top gives me f prime of x equals 1, and g prime of x equals 2x. So that makes the derivative, I'll say df dx, is equal to low d high x squared plus 1 d high, which is 1, minus high d low x minus 5 times 2x, square the bottom, and away we go. So this is my derivative, and I'm going to simplify this a little bit just for ease. So this 1 doesn't matter, so this is just x squared plus 1 minus, and then if I FOIL this out, I get minus 2x squared minus 10x. All of this over x squared plus 1 squared. So this is my derivative. And now I am going to plug in my point 1 comma negative 2. So this whole thing is my derivative as a function. So this tells me the slope of my original function at any single x value. But to find the slope at a particular x value, I'm going to plug in the x value that I'm given, which is x equals 1. So I'm going to say m sub tan at x equals 1 is equal to, plugging in x equals 1 gives me x squared plus 1 is 1 plus 1 minus 2x squared is 2 minus 10 over 1 plus 1 squared. This gives me 2 minus 2 plus 10, which is 10 over 4, or 5 over 2. Oh, sorry, 5 over 2. So my slope is 5 halves. And now to find my tangent line equation, I'm going to plug this into y equals mx plus b. So y equals mx plus b. My y value is negative 2. Negative 2 equals, my slope is 5 halves. My x value is 1 plus b. So I get negative 2 equals 5 halves plus b. And subtracting 5 halves gives me negative 9 halves equals b. So the equation of the tangent line is y equals 5 halves x minus 9 halves. So here we had to use the quotient rule in order to find my derivative as a function. Then I plugged in the point to where I wanted the derivative, which was the point 1 comma negative 2. I found the slope of the tangent line, and then to find the b value, I plugged in all the information I had into y equals mx plus b. All right, so the next theorem is super handy, and I don't know why the textbook doesn't introduce this earlier. So in section 3.3, we learned the power rule, which is the derivative of x to the power of n is equal to n x to the power of n minus 1, but we only learned this for non-negative integers. So n needed to be a non-negative integer, but actually this is true always. So no matter what n is, if it's negative, if it's a fraction, no matter what n is, this is true. So this is true for any real number. We no longer have to do the thing where it's only non-negative integers. So for example, if I wanted to take the derivative of the cube root of x, this is equal to the derivative. Rewriting the cube root of x as a power is x to the power of 1/3. So then according to this power rule now, I can bring this 1/3 out in front and subtract 1 from the power. So this gives me 1/3 x to the power of negative 2/3, which we can simplify as 1/3 cube root of x squared. So this is very handy. Obviously, we can use this for square roots now, any kind of root. Yeah, n can be any number now, so this is very handy. Okay, lastly, we want to find this derivative. We have a function f of x equals 3x times e to the x over x squared minus 2. So here we are going to have to use both the product rule and the quotient rule, and you'll see why. So first of all, I do have a quotient, so I need to be careful about what I pick for my f and my g. So my f will be the top. F of x equals 3x e to the x. But then to find the derivative of this, I'm going to have to use the product rule. So f prime of x equals, so I take the derivative of, I take the first chunk here, 3x times the derivative of the second chunk, which is just e to the x, plus the second chunk times the derivative of the first. And this factors easily. We can factor a 3e to the x out of each one of these terms. When I factor out 3e to the x, I am left with x plus 1. So this is f prime of x. We had to use the product rule here. And then g of x is my denominator, x squared minus 2. And our g prime is easy to find, it's just 2x. And now I just use the quotient rule as normal. So I see that the derivative of 3x e to the x over x squared minus 2 equals the derivative of the, the bottom, so I low d high, so x squared minus 2 times the derivative of the top, which was 3e to the x times x plus 1, minus the derivative of the, the top, 3x e to the x, minus, times the derivative of the bottom, 2x, over x squared minus 2 squared. And just to make this a little bit neater, I'm going to factor out a 3e to the x out of each of these terms. So if I factor out a 3e to the x, I am left with x squared minus 2 times x plus 1 minus 2x squared over x squared minus 2 squared. So this is my derivative. So this quotient rule and product rule make it so that we can take the derivatives of many, many more functions now. Before we could just take the derivatives of things involving e to the x and polynomials. Now we can take derivatives of products and quotients of functions. So we will be using these for the rest of the term. They are very important. So if you're not super comfy with them now, I would do some more practice, either on the online homework or otherwise let me know if you'd like to see some more examples. But that's it for today. So hope you have a great day and I will see you next time.